This conference will now be recorded.
All right, perfect. All right, guys. So, sorry, I had to plug in my Apple Pencil because, it's been getting a lot of use lately. All right. So, so much spirit in one room. Yeah, hey, look at that. Isn't that cool? Look at that. Little rowdy. I don't know if you guys can see this, but this distillation setup, there's a mixture in here and then it's doing a purification, so it's coming out as just green. You're going to learn about what this monstrosity is next semester. And then most of this other stuff is from organic too. So yeah, a preview of what to come. All right, guys. So let's go ahead and get started. Now, again, this is for you guys. So if you have any questions, just feel free to interrupt me. And that's no problem. The first thing I'm going to do is I'm going to start with the roadmap, just because it's easier for me to import it and leave it at the top of the PDF than put it down here. All right, and so the NMR for the roadmap is on the next page. And when you go over to this NMR, if anybody's looked at this, it looks pretty damn intimidating, doesn't it? Well, it is, except for one thing. Sometimes I'll give you a hint. Okay, so polar product solvent, right? This is what? This is a nucleophile. So whatever I have over here is most likely going under an SN2 reaction. And the nucleophile is going to be this entire chunky. And so that's not unusual for me to give you guys a little bit of a hint, okay? A little bit of a hint. So coming back down here, I know that part of my structure is going to be this, right? Because why? Because that was a nucleophile, okay? Which means what? I've got almost everything that I need to know to get this solved, okay? I know that this CH2 is going to be a triplet. It's going to be fairly downfield because it's next to the oxygen atom, probably that one. And then I know that this CH3 is going to be a quartet. I'm sorry, it's going to be a triplet, not quartet. And it doesn't matter whether you call it this one or this one, but we're going to find out later it's most likely this one because of its proximity to the oxygen atom. But again, when I'm asking you guys to solve these roadmaps, I'm not asking you to identify all the protons on the NMR, so it doesn't matter. Okay, it really doesn't matter. Okay, this I don't have to worry about because why? Well, I'll obviously have a orthosubstituted benzene derivative, but again, my nucleophile was that. So then I have what? I have a series of CH2s, 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 and then a CH3. Okay, and so what is this? Well, this CH2 here is downfield, so that's probably the CH2, okay, that's attached directly to the oxygen atom, right? Something was substituted, right? I have up here, if you look at this, I have a tosylated species, right? I have a tosylated alcohol, which means that this is basically going to turn into a leaving group. I did a leaving group, so you could treat it like iodide or bromide or chloride, it doesn't matter, but it's a leaving group. And I reacted it with this. So whatever was attached to this tosyl group is now attached here, right? And so CH2, okay, probably this one, okay. Next is going to be another CH2. How do I know? Oops, shit. Totally screwed this one up. Hold on. Sorry, I've been doing shit all morning. And it's been one of those weeks. My bad. So let me go back just a second. This CH2 would be a quartet. And that is the CH2 next to my CH3 down here. My bad. All right. So again, going back. Okay. This CH2 would be a triplet, which is that guy right there. Okay. How do I know he's next to a CH2? Because he's a triplet. And frankly, everything else I have left in my NMR are CH2s or CH3. And so if I attach the CH2 directly to a CH3, first of all, he wouldn't be a triplet, and then I'd be done. Okay, so this CH2 is probably this CH2, and he's a pentet, which means he has 4 neighbors. So CH2 on one side, CH2 on the other side. CH2, okay? And again, as I get further and further away from the oxygen, these protons are going to shift further and further upfield, okay? This CH2 is a pentet, again, so obviously he's next to another CH2, okay? This CH2 is a hextet, okay? It's my last CH2, and he has 5 neighbors, so probably a CH2 and a CH3. And the only thing I have left, of course, is this CH3 here, okay, there. And so my structure is this guy here. And you know, you don't have to go and redraw it, but I'm just going to do it because 1, 2, 3, 4, 5, and then that's my structure here. And again, this would have been a very complicated NMR had I not given you this massive hint. Okay, so I'm just going to paste it here. And so this was, okay, not that was, but that is what I added. Okay, and so after that, it's just what? Okay, adding in the structure. So 1, 2, 3, 4, 5, OTS. Okay. You see tosyl chloride, don't look at this molecular formula. It's going to freak you the hell out. Okay, unless you remember that this is the molecular formula for tosylate. A lot of times the molecular formula will freak you out, and you'll spend all this time trying to figure out where to put everything. Okay, this is going to undergo an elimination reaction. Okay, what did I react with this tosyl chloride to get this tosylated species? Well, the only thing we know what to react with is alcohols. Okay, then I reacted this alcohol in the presence of some HX. Okay, most of you guys knew that you were supposed to tell me what the atom was, but a lot of you guys didn't, so you need to make sure. I have a 3-to-1 ratio, which means it's chlorine. Okay, HI, we don't have any really interesting isotopic distribution for that. Okay, and then this over here, I probably shouldn't have used this here, so switch this over to THF. Okay, and so I have a primary alkyl halide. Okay, I have a small, strong base, so we know that it can undergo either E2 or SN2. And so which product do I want? Well, if you look at the molecular formula real quick, I have an oxygen atom in there. So obviously I'm looking for what? I'm looking for the Williamson ether synthesis product. And that would be that there. Okay, that would be that there. All right, questions? Hold on just a sec. So what I'm going to do now is I'm just going to go through the entire book, not the entire book, all of chapter 9. Sorry, I had to clean up my office before the thing today, so usually I have all of this stuff right in front of me. All right, so going over all the key reactions. By the way, you guys are going to be responsible for melting points, boiling points, good stuff like that, physical properties. Okay, I'm not going to ask you any nomenclature because, again, all you have to do is Google. Okay.
Jordy, I have a question for you.
Yes, ma'am.
Is there a carbon missing on the where the iodine and the chlorine is? So there's only 4 carbons. Shouldn't it be 5?
There.
Okay, thank you.
Yep. Okay. So the first thing we talked about when we talked about chapter 1 is turning our whatever it is into a good leaving group. Okay, and so with alcohols, there's a couple of different options. We can use acids, right? And so alcohols with HA. Okay, if I use sulfuric, tosyl sulfonic, okay, it's elimination. If I use HX, it's substitution. Okay, And so we're just going to go over some of these real quick, but say I have this primary alcohol here. I'm going to react it in the presence of tolyl acid. Okay, if I ask you the mechanism for this, okay, for primaries, it's E2, secondary, tertiary, it's E1. Okay, so again, it's a concerted reaction mechanism, but it's a concerted reaction mechanism once I form my good leaving group. Okay, so I'm going to have this right here, deuterium atom here. Okay, tosylate will come and remove the beta proton, form my pi bond, eliminate my leaving group, and that's going to be the product there, an alkene. Okay, obviously something that's key here, if I have this compound here, okay, H2SO4, I'm only going to form this alkene here. I'm not going to form any other products because why? Okay, there's only one beta proton to be eliminated because it's primary, right? Primary alcohols only have one neighbor by definition. Okay, the carbon only has one neighboring carbon by definition. It's primary. So I'm not going to see any carbocation rearrangement because why? Well, I don't form a carbocation. It undergoes an E2 mechanism. Okay, and so be careful of that because I might ask you something like this on the synthesis portion. Okay, and so make sure that you use the correct conditions. And if I ask you why there's no rearrangement, you need to make sure that you say we only form rearrangement, or we only have rearrangement when we form carbocations. We don't form a carbocation, there's no rearrangement. Okay, secondary is when it gets interesting. Okay, say I have this alcohol here, going to react in the presence of sulfuric acid. Again, before I do anything, I must turn my OH into a good leaving group. That is key. That is the most important first step. It's very important. Okay, my leaving group will leave. Okay, now I have a carbocation. Okay, but you always must remember that before any type of rearrangement, don't forget to eliminate any beta protons before rearrangements. There's always going to be product before and after rearrangement. Okay, I'm not going to go over the whole mechanism unless you guys want me to or you have specific questions. Okay, but suffice it to say, okay, I'm going to get this product. Oops, that would still be a wedge. I'm going to get that product and this product here. Okay, so that's before any rearrangement. I can have a 1,2 hydride shift, right? That's going to form this carbocation. And the hydrogen that I just shifted can also be eliminated. But either one of these two beta protons, which are identical, can be eliminated. And so after the shift, I can form the same product that I formed before. And then I'm going to have a product that I can form after the shift. Okay, and again, if I ask you for the mechanism, you have to show me all of them. Okay, you can't just pick and choose. Okay, you can't eliminate all of these protons at once off of this species. Okay, all right.
Professor, quick question.
Yes.
On that first product that you made with the double bond all the way to the right, would that be on the second
What happens when I rush?
Okay, cool. I was like,
yeah, that would be a beta. I'm sorry, gamma proton elimination.
Okay, thank you.
All right, so Other types of rearrangements. We can have alkyl shifts, right? And so again, say I started with this alcohol here. React in the presence of tosyl sulfonic acid. Form my good leaving group. Okay, it leaves. Okay, form this carbocation here. I have beta proton elimination. Okay, and this is going to form that product there. Okay, easy sneezy, right? But then I can also have what? Okay, after again I form my carbocation, then I can have an alkyne shift or an alkyl shift. Okay, it's going to form a tertiary carbocation, which is more stable. Okay, there was a beta proton here that we didn't draw at the beginning. Well, obviously it's still here. And then of course I have these two beta protons here. So again, making sure that you always draw the product both before and after any rearrangement. Ah. So for this particular reaction, there's going to be what? 1, 2, 3 products. Okay, remember, during a hydride shift, you're going to have a product that can form 2 different ways, before and after rearrangement. An alkyl shift, you're not going to have a product that can form before and after. Okay, just not seen. All right. So say I gave you this on the, yes, go ahead.
On the problem you did right before this one, the purple beta hydrogen all the way on the left, is there a reason we're not seeing a product for that?
So if I were to eliminate this, right, I would get this, which after a rotation
Oh, it's the
will
same.
give me that
Okay,
one.
yeah, got
Yeah,
it.
because
Okay.
yeah, but here's the deal. If if you're not sure if they're the same or they're not the same, you can write them both down. I will never take off points for writing this correct answer more than once. Okay, so if you're unsure, then err on the side of caution and just go ahead and write it down. Okay, and you'll be fine. Okay. All right.
Professor,
Any more?
are you recording
Yeah,
it?
I am. Thank you. Okay. All right. Any more questions about this?
Professor
So let's
Gordy,
take a, yes.
sorry. So you said an alkyl shift. Is that the same as a methyl shift?
Yeah. So when we see alkyl, basically what we're talking about is a methyl shift. And you can see an ethyl shift, but that just gets crazy. So I think she only talks about a methyl shift or a ring expansion. And so those are the only ones you're really going to see on the exam. Okay.
Can you
All
go
right.
over hydride shifts one more time?
Say that one more time.
Can you go over hydride shifts one more time?
Like,
Yeah, for the second one.
so
All right.
what is your question about it?
Just the whole process and what to do with it. Yeah.
So okay, I don't mind real quick, but I don't have a whole lot of time to spend on it because I have so much other stuff to cover. But anytime you form a secondary alkyl carbocation and you have a tertiary hydrogen, you can see a hydride shift because why? By shifting that hydrogen, you now have a tertiary carbocation. And their relative stabilities are just so much different. In other words, a tertiary carbocation is so much more stable than a secondary carbocation. And so that's why these are observed. Okay. And if you need more than that, I suggest you watch the video and the office hours from Tuesday. I go on to these in very great detail. And so it's almost 3 hours of me explaining this. So it's pretty thorough, the explanation. Okay. All right. Again, what if I give you this? and I ask you to show me how to form this. Okay, and again, some of you guys may be wondering, you know, what about all the other products that you can form? I will stipulate to the fact that there are several products that you can form. Okay, but when I give you the product that I want to see, I don't want to see any other mechanisms. I don't want to see any other mechanisms. Okay, you got enough time. Okay, and so this is kind of like what I just showed you. The only difference is what? The only difference between a protonation of an OH, we're going to protonate this alkoxy group. Okay, and so of course, anytime you have an ether or an alcohol and an acid, or even in that case, even if you have an epoxide, anytime you have an oxygen atom and a strong acid, you protonate. You form a good leaving group. The leaving group goes. Okay, and so now what we're going to have is we're going to have this so-called ring expansion. Now, like I told you guys before, I'm always going to give you some sort of anchor. In other words, I'm always going to give you guys something so you can get your bearings. You can keep your wits about you. Okay, this group right here is that group right there. Okay, where the ring forms, okay, this carbon where my anchor is coming off of is going to be the carbon that was my original carbocation, my original. We're going to form another carbocation, but that's going to be the first carbocation that I can form. Again, like I told you guys in the past, let's just go ahead and number all of my carbons. 1, 2, 3, 4, 5, 6, 7, 8. I didn't number this methyl group here because why? Didn't really need to. Okay, but you can number it if you want, because I'm pretty sure that that methyl group is that methyl group there. Okay, and so what do we need to do? We need to do a ring expansion. Okay, and it's looking like, in addition to a ring expansion, we might also have a hydride shift. Okay, and so I know I need to form a 5-membered ring. I know I need to form a 5-membered ring. And so I'm going to either break one of these 3 bonds, okay, 6 and 8, 6 and 7, or 7 or 8, okay? And which one of these bonds am I going to break? Count out. 1, 2, I can't, 1, 2, 3, 4, 5. So if I break 6 and 8, that'll give me a 5-membered ring, okay? But where does that put my carbocation? Exactly, it puts it at 6. Is that a good place for my carbocation to be? Is it? It actually is a good place for my carbocation to be. Okay, it actually is. Because here's the deal. If I do this, okay, if I do this ring expansion, okay, so I know that this is carbon 4 here. I'm just going to say it's carbon 4 here. Okay, and then 3, 2, 1. All right, I'm going to go ahead and I'm going to just number my carbons. 1, 2, 3, 4. Okay, what did I just form my new? Yeah, the hydride bond. Yes, exactly, Christina, the hydride shift. What did I just form my new bond with? 4 and what else? 8 and 4. Very good. So I'm going to make this carbon 8. Okay, 7, 6, and 5. So I know on 7, I have my methyl. Okay. And so where does this put my new carbocation? Where does it put it? That's exactly right. 6. Good job, guys. Because I broke this bond here. Carbon 8 took the electrons with it to form the new bond with carbon number 4. And so now I have my new carbocation on 6. I'm not quite there yet. I need to do hydride shift. Okay. Now I have my carbocation here. Now I can do beta hydrogen elimination. So bisulfate will come and remove. And that'll give me my final product. Okay. Questions about that?
I had a question. So
Uh-huh.
whenever you see the carbocation on a secondary, it's secondary, would we do the hydride shift?
Okay, so a couple of things. First of all, only if you can move a tertiary hydrogen over, all right? So if I have something like this, secondary carbocation, but both of these hydrogens are what? They're secondary as well. So if I do a hydride shift, what do I gain energetically? Nothing. I gain nothing. I went from secondary to secondary. And so this is not observed. Okay, this is not observed. Okay, and so, yeah. But again, when I give you a ring expansion problem, right, and you're going to have one of these on your exam, I'm going to ask you to go from here to here. And so it's one of those things that we say by inspection, this is what I have to do. And how do you know I have to do it? Because if you would have just done the ring expansion here and then stopped at this step, there's no way you could have created that pi bond right here. It just wouldn't have happened.
Also,
Okay.
I have another question.
Uh-huh.
Instead of the hydrogen being on that tertiary carbon, if
I'm sorry,
there
could
was
you
a
start over? My air conditioner just turned off and it was making a god
you're
awful.
good.
I'm sorry.
So instead of the hydrogen being on that tertiary carbon at number 7,
Uh-huh.
let's just say another methyl group, then we could do a methyl shift from
I
7 to
mean,
6.
theoretically, if I were to give you this, right? If I were to give you this here, right? And then I would ask you to go here. You would have to know that the only way I could get to that product would be through a methyl shift. You see what I'm saying?
Yeah.
And
Got it.
so, yeah, and so how do you know what to do? Well, it depends on what I give you, honestly. By experience, by having done, you know, some of these problems, by working through them. So yeah, at some point I would have formed this carbocation here. I'm not going to go through the entire mechanism, but at some point I would have formed this carbocation here. Then I would have had to do a 1,2 methyl shift. Okay, and that would have given me this here. Now my carbocation would be here, and then of course I'd have to do beta elimination to give me that. So yeah, it depends on what I give you, honestly.
So far we'll be doing ring expansions, but what if, are you going to give us a question where we have an expanded ring and instead of expanding it, we're closing it?
I might.
Okay, thank you.
But hey, I would tell you, in other words, it would be something like this. Like, how would I go from here to here? And that would be easy, right? Deprotonation of my proton. Formation of this species here. Intramolecular SN2 reaction, like that. But if I wanted you to go that route, I would say go from here to here. In other words, you don't have to guess. Okay? You would not have to guess about either a ring closing or a ring forming or a ring expansion. Okay? Okay. All right, so let me ask her. Oh, come on. You got to be kidding me. This is like the easiest freaking problem in the world. Is that what you're talking about? Humphreys? It's not that bad. All right, Fahad. What bond stress? I don't know what you're talking about. Which bond stress? Okay. All right, so what classifies as a hydrogen as a beta as opposed to an alpha hydrogen? Okay, so we saw this last time. If I have a carbocation here, this carbon is referred to my alpha carbon. It's just the way we call it. Okay. And then as I move over, I go alpha, beta, and then here I would even have a gamma proton. But, you know, alpha, beta, gamma, delta, blah, 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 blah. Okay. And so to have beta hydrogen elimination, right, I have to form a bond between this alpha carbon and this beta carbon. So basically these electrons will just collapse in. Or I can have it shift from a beta hydrogen. Okay, we don't shift gamma hydrogens. We don't shift delta hydrogens. It's got to be a 1-2 shift. Okay, it's got to be a 1-2 shift. Okay, all right, let's move on. Again.
Hey, I have one more question.
How
did you decide that the 8 and 6 bond was the best bond to break?
By looking at it.
Just because it's bonded to more and the.
Because that's that by breaking that bond, that gives me my carbocation on carbon number 6, and that's kind of where I needed it to.
Okay, sounds simple enough.
I mean, there is a certain amount of what we call by inspection, right? What does that mean? You got to look at it, right? You got to look at it and see what gives you what you want, right? And so if I would have broken, okay, the bond between, say, 7 and 6, for example, okay, I would have formed a new bond between 4 and 7, right? And then that methyl group would be here. See what I'm saying? And this would be 6. Wait, hold on. 4, 5, hold on. 4, 5, 6, 8. And then my carbocation would have been here. So it's one of those things that we say, how do you know how to do that? And my advice to you is practice and by inspection, by looking and seeing what doing one thing will give you. Okay, experimentation. And, you know, hey, it's a chemistry class, so why the hell not?
So the point of doing a hydride shift is to change a secondary carbocation to a tertiary?
Yes.
Okay.
That's the whole purpose of it, to go to a lower energy state. Obviously, this is an alkyl shift, right? When I open up this ring here, so when I do this ring expansion, it's a form of an alkyl shift. Okay, it is a form of an alkyl shift. But so in this particular problem, we had an alkyl shift and then a hydride shift. Okay, but guys, I'm not going to give you anything like that unless it's a problem like this. Okay, in other words, I'm not going to give you a question, draw me the mechanism, and leave it blank, right? And then expect you guys to know you should do a ring expansion, then a hydride shift, then an alkyl shift. No, it's going to be very straightforward in what's the mechanisms. Okay, all right, we really do need to move on. All right, so take my alcohols, I reacted with HX. Again, now we can introduce methanol because it's substitution. Primary, okay, it's going to be SN2, but it's going to be slow. Okay, secondary, tertiary, SN1, no elimination, no E1. Okay, just like when we had E1 just right now, we don't have any substitution. Okay, and so again, the mechanism for this is the first step is what? You have the formation of a good leaving group. So now I'm going to use HBr. I'm going to form a good leaving group. Unlike before, okay, I now have a base that can act as a nucleophile, right? Tosylate and bisulfate are too big and bulky, so they can't act as nucleophiles, but bromide can. And so what I'm going to get is I'm going to get an SN2 reaction to make sure I'm also going to have inversion of my chiral center. So again, it's an SN2 reaction. It's concerted, okay, but this particular mechanism, of course, has this initial step of forming the good leaving group. So it's a double humper. Okay, it's a double humper. Okay, and so again, what can we see? Excuse me. Say I have this guy here. Going to react this with HCl. Formation of my good leaving group. Because, oops, shit, I can't believe I just did that. Leaving group leaves, okay? And so now, I'm going to have what? I'm going to have this carbocation here. That can do a couple of different things. First thing, chloride can come and attack. Then I'm going to form this guy here. Okay, no stereochemistry because I formed a carbocation. Okay, the second thing that can happen is I can have a hydride shift. And so what that does, that makes this methyl here go flat, and this carbocation here is now here. And then again, chloride comes in and attacks. Obviously no stereochemistry. Okay, the next thing I can have is what? A methyl shift. Okay, so what is that going to give me? Well, the methyl that just shifted is shifting over into an sp2 carbon, so it's going to be in the plane. This other methyl that didn't shift is going to now be on a dash because I'm sorry, on a line, because why? Well, now it's sp2 hybridized. And again, chloride could come and attack, and so this would give me this product here. Okay, and so anytime you form a carbocation, we didn't talk about this in chapter 7 and 8, but anytime you form a carbocation, if it's secondary, it can rearrange. I didn't want to drop that on you guys because, you know, getting enough shit dropped on you that day or that week or whatever it was. Okay, So questions about this? Is there a wedge missing? Thank you very much. I did miss that wedge. Should have stuck to the cut and paste. All right. Any more questions about this? So what if I don't want rearrangements? You know, what if I think rearrangements suck? Okay. What if I needed to form a single product? Well, then we have Pockle phosphoryl chloride that will give me E2 only. Okay. I have phosphorus tribromide and sulfuryl chloride, SOCL, which will give me SN2 only. And so Pockle is an eliminating agent. PBr3 is a brominating agent, and thionyl chloride is a chlorinating agent. Okay. And so these will allow me to turn my hydroxy group into a good leaving group, but I don't have to worry about any of the rearrangements. So again, going back up here, if I were to take this same species here, okay, and react it in the presence of PBr3, okay. For those of you that watch the videos, you know that this phosphorus is electrophilic. Nucleophilic attack kicks off a bromine. I'm going to have this entire species here is my leaving group. The bromide that I formed in this step right here is going to come and do a backside attack. Very slow backside attack, but a backside attack nonetheless. Okay, and so this right here will be my only product. And I have stereoselectivity. Say for whatever reason, I wanted to chlorinate this instead of brominate it. I'm going to use this in the presence of thionyl chloride. Thionyl chloride, this reaction needs to take place in pyridine. Okay. Thionyl chloride is also electrophilic. First step of this, of course, is nucleophilic attack of the sulfur. I'm going to kick off my halogen. I'm going to form this intermediate species here. Oops. Okay. And pyridine is the key. When I have pyridine, that's when I know I need to do a deprotonation step. So I'm going to go ahead and do that. That's going to give me this guy here. The chloride that we formed again in this step right here is going to come back here. Okay. I'm zooming this up because I want you guys to see my flow of electrons. This bond right here is going to break, and oxygen and sulfur will form a pi bond together. Chloride is kicked off. And so what I get here is still an SN2 reaction. But what's important here is the driving force of this reaction is the formation of sulfur dioxide, which has this structure here. Okay, so that formation of that gas. Okay, and again, I have a secondary substrate, so I can go ahead and I can do an E2 reaction. So this is where Pockle comes in. So again, Pockle takes place in the presence of pyridine. Okay. I know that you guys are going to have your notes in front of you, but next semester when you're taking whatever exam, when you don't have your notes in front of you, Pockle and SOCL, a lot of my students confuse them together or confuse them. I know the S actually stands for sulfur, but the way to remember is the S stands for the substitution reaction, whereas phosphoryl chloride will give you elimination. So again, the mechanism is very similar in all three of these. Nucleophilic attack, okay, formation of an intermediate species. We're always going to kick off the halogen. So here I'm going to have HPOCl2, positive charge. I forgot my pyridine, and that's important for the mechanism because pyridine will then come in and do a deprotonation step. Okay, and so now I'm left with this. Pyridine is also going to do double duty. It's also going to do beta hydrogen elimination. And so it's going to come over here, eliminate this beta proton, form the pi bond here, kick off this leaving group. And so unlike the hot mess I got, and I actually just realized I think I forgot a couple of products with the earlier one. Okay. This is my only product for this particular reaction. Okay. And so I just realized that when I did my method shift, I should have had one more too. Hold on. Oh, never mind. I'm good. I did a substitution on elimination. Probably did that on purpose. All right.
Does PBr3 not need a solvent?
It does have a solvent, but we don't add a solvent. And the reason we don't add a solvent is everything takes place in the solution, right? But the reason we don't put any solvent in there, honestly, is because the main difference between Sockle and Pockle versus PBr3 is pyridine deprotonates before the leaving group leaves. And so I don't know if she did it so that you guys could keep the mechanisms straightforward. I mean, that's why I do it. And so it's always implied there's some sort of solvent. And so what you need to focus is on not on the solvent in this case, and the fact that it is PBr3, and PBr3 is a brominating agent. All right, I'm gonna let you guys catch your wits for a little bit, okay? But is there any other questions?
I have a question. If
Yes.
Pockle and Sockle don't have pyridine, then there's no reaction?
If I've done my job, it will have pyridine underneath it.
Okay, sounds good.
And then in the action that you just did, you would have to do the substitution and elimination together?
For which one?
For you used Sockle, and then you said since there was a secondary substrate, then you did elimination with Pockle.
No. So Sockle only gives you SN2, so no elimination. Okay, no elimination. And so these are three separate reactions. So this would be reaction number 1 under this condition. This would be a reaction number 2 under these conditions, and this would be reaction number 3. And so Pockle only gives you E2. PBr3 and Sockle only give you SN2. And so these two reactions are not going together. These are like,
oh,
does that make sense?
Yeah, I get it.
Yeah, this is like I took my flour and I made a cake, and this is like I took my flour and I made a bread.
Okay, I was just confused because you used the same one, so I thought they went together, but I get it. Thank you.
Yeah, I was just using the same one because I didn't want to have to draw different ones, and my brain's a little fried right now. Was a lot of people having that same confusion? Oh, I'm sorry, guys. Yeah, it was the same starting material with 3 completely different reactions. My bad. My bad. Like I said, it's like we have flour in our pantries right now, and we can take our flour
Question, I was doing some problems from the back of the book, and maybe I'm missing something, but I'm confused when, like, say for your earlier example with a secondary alcohol being treated with HCl.
Uh-huh.
And then it forms the carbocation, the secondary carbocation.
Uh-huh.
Yeah, I know you said that there's no stereochemistry after that. You just add the chlorine in the plane. But in the problems, there is stereochemistry after the secondary carbocation. So I'm getting a racemic mixture.
Could you tell me the problem number?
It's 9.45, letter F. Again, maybe I'm just missing something.
You mean in the answer she has stereochemistry?
Yeah.
She should not have any stereochemistry in the answer for A, E, or F. A,
Okay.
E, and F would give you no stereochemistry.
Okay. All the answers have stereochemistry, so I guess, do I just erase that from my brain?
Yeah, sorry about that. It must be typos in the solutions manual. You got that from the solutions manual?
Yes.
I'll look into that and then I'll send Janice a little email.
Okay. Thank
Yeah,
you.
I'm sorry about that. Yeah, anytime you have an acid and a secondary or a tertiary, I mean, here's the deal. Anytime you have an acid and a secondary or a tertiary substrate, you are going to form a carbocation. Once you form that carbocation, all stereoselectivity is out the door because you can't, right? You can't have a backside attack if I can attack either side,
Okay.
I did have one question.
Oh, it says racemic. Hold on. It says racemic in the book. Oh, so I think what she did is she might have drawn one stereoisomer and then just said racemic, so the other one is implied.
She drew both.
Well, that's because you do get both.
Gotcha. Okay.
Yeah, I mean, so when I draw this, hold on just 1 second, guys. When I draw this, say I did the substitution of this alcohol here with HBr, when I draw this is implied.
I see. Okay.
Yeah, and so I know I mentioned that, but it's not like you're not taking in 50,000 pieces of information every day. Expect you to catch them all. Yeah, and that's what she meant, and that's what I mean when I draw the straight line.
Perfect. Okay, thank you.
Yeah, you're welcome. Okay, who else? Somebody else had a question.
I had a question. I was doing problems from the textbook as well.
Mm-hmm.
For 9.17. Let me see. When I was doing them, I assumed for B that it was gonna be.
Hold on. Let me get there.
Sorry.
That's okay. Because that's the in chapter questions, right?
Yes.
Okay, hold on. 9.17. Can I not see these? Sample problem 9.8. Jesus Christ, where is it? I can't. My book only goes to sample problem 9.8. And then
it was within the in chapter. It's on page, let me see. Give me 1 second. Oh, well, I have the online textbook. I don't see page numbers actually.
Anyways, let's do your best and see if I can figure out what you're asking.
It says, what is the major product formed with each alcohol is treated with HCl? And then, I'm sorry, 9.18. Oh, but on here it says 9.17. Well,
Could you just
it
take a
was like
picture
with
of it and send it
8.
to me? And then with your
Yes.
question, could you do that? I think it might
Yeah.
be.
Yes, we can just move on.
Yeah, send it to me in the group
I'll
me, okay?
send it.
And then I'll answer it
Okay.
in a second, okay? I promise. All
Okay.
right,
Thank
guys.
you.
So the last type of reaction that we're going to talk about with, oh, and I always forget this one. This was a new reaction that was introduced, I think, in the other edition that I always forget about. With zinc chloride. So again, I always forget about this one. Zinc chloride. Right? She uses zinc chloride. What does she use? Zinc chloride and what else? I can't even find it anymore. See? Nobody gives a shit about that. See, it's not even in the reactions of alcohol section. It's such a new reaction, she hasn't even added it to the back of the book. Okay, oops. And so this will also give you an S&T reaction with a chlorination. Okay. All right. So tosylation, tosyl chloride, triflation with triflyl chloride, and methylation. Don't you just love all these words? It's almost like we made them up, because we did. Okay, with mesylate chloride. Okay, now this is a little different, okay, than what we've talked about right here. We turn our alcohol into a good leaving group, but we leave it like that. And in other words, we make this and then we stick it on the shelf. Anybody ever know what friendship bread is, right? Anybody ever gotten on the receiving end of friendship bread? If you don't know, somebody that hates you makes this for you. Okay, and then you take it and then you bake part of it. Okay, but the rest you just put into your refrigerator for future use. Okay, and so what we're going to do is we're going to prepare a substrate, but then we're just going to kind of put it on the shelf. Okay, in other words, we're going to use it for another reaction further down the road. Okay, and so I'm going to use triflate because it's easier to draw. Okay, so a triflyl chloride, which is this guy here. Okay, this reaction also takes place in pyridine, and again, anytime you see pyridine in this chapter, pyridine is going to come and do what? It's going to come and do a deprotonation step. Okay, and so just like all of these other ones, nucleophilic attack of either sulfur or phosphorus, and whatever halogen is directly bonded to them, it gets kicked off. Okay, I'm going to form this substrate here. At this point, you can go ahead and use the abbreviations. Okay, but you have to draw the product, or I'm sorry, you have to draw the structure for this step here. And over here, once I know that you know the product or the structure, feel free to use the abbreviations. Okay, then I'm going to get this, and it stops. Okay, this reaction stops. Okay, I'm going to make this in my lab, and I'm going to put it into a little jar, and I'm going to throw it on the shelf for future use. Okay, and so you can do, it's the same thing with all of these guys. The only difference is the R group, but the mechanism is exactly the same. For tosyl, the mechanism is, or the R group is this called a toluene group, and of course for the methyl, it's a methyl group. Okay, all right. So what do we do with this stuff? So again, it's all about synthesis, right? So say I needed you to make two batches, and I needed my batches to be enantiomerically pure. Okay, I needed my two batches to be enantiomerically pure. So we start with this alcohol here. And I said, okay, I need you to make me a little bit of the R and a little bit of the S. Okay, and you know, because you're a gifted chemist by now, is purifying a racemic mixture at the end of the day is a pain in the butt and expensive. And so here I have inversion. And so I know that I need to do an SN2 reaction. Okay. Here you're probably looking at this and you're saying, well, there was no inversion. Well, there was, but it was a double inversion. Okay. And so when you look into your arsenal, right, I know that if I use tosyl chloride, trifluoro chloride, or methyl chloride, the reaction stops. And then I can then react this with a nucleophile under SN2 conditions. Get a single inversion. I know that if I do PBr3 or Sockle, I get an inversion, but chloride and bromide are both good leaving groups, so I can do a second SN2. And so when you have a so-called double inversion, you're doing what? 2 SN2s. Okay, when you have a single inversion, you're only doing 1 SN2. And the way to approach this problem would be something like this, where I could do 1 TSCl pyridine. Do not forget to add your 1s and your 2s. Second one, sodium acetate would probably not be a bad idea. And because it is secondary, you need to tell me that the solvent that you're choosing is polar aprotic. Okay, and so this pathway would give me this. Okay, oops, sorry. And then this. That would give me that and then that. Whereas this pathway, I could use Sockle, pyridine, or if you prefer, PBr3 or zinc chloride. So any of these substrates will give me halogenation under SN2 conditions. All of the halogens will give me what? A good leaving group. And then again, part 2 would be exactly the same. And so again, the difference between these two mechanisms is at first, I would substitute off the hydroxy group, invert the chiral center because my halogen would come in and do a backside attack. And then of course, I do a second SN2 reaction, okay, and I would get that. Okay.
How did you know double inversion?
How did I know it was a double inversion? Because I know, here's the deal. I can't do this, right? I can't form this intermediate species here because why? Like I can't just do this. I can't just take my oxygen. Oops. Come on. I can't just take off my OH. In other words, we cannot just remove this and leave the bond there. So anytime you break a bond in this class, two things are going to happen. You're either going to invert the chiral center, right? Or you're going to form a racemic mixture, right? Because we're doing substitution. Okay. And so you can't just go from here to here. It can't be a one-step reaction because my nucleophile is going to come in and do this. Oops. And do this. And so this step is going to give me inversion. Okay. And so to do another step, to get it back to being a wedge, I have to do a second SN2 reaction. And that's how I knew. I know that I can't go wedge to wedge. I know that. And so I have to go wedge to dash back to wedge. And it's a two-step reaction. Okay. And so that's important. Did that answer your question?
So
any more questions?
So anytime you see going from a wedge to a wedge, you know that there was two reactions?
Two SN2 reactions.
Yeah, okay.
Yeah. How do we know if it's a double inversion if no products are present based on the information I give you? right? Say I gave you this in class, or say I gave you this on the exam. Say I wanted you to go from here. Say I gave you, I'm sorry, say, and what's the products? I gave you, oops. Okay, I gave you this, and then 2, I gave you, I don't know, and so that's how you would know it's a double inversion, because you would recognize both of these reactions as being SN2 and SN2. And so the answer would be something like this. Step 1, okay, and then step 2 would be this, and that's how you would know.
So back up at the top where you had the nucleophile attacking on and the OH group leaving, that would have had to been OH2, right? To have been the leaving group. Yes.
I mean, not necessarily. It would just be well, obviously, that was not the point of that conversation. Obviously, I would have turned it into a good leading group first. And it would not be OH2. And why wouldn't it be OH2? Because OH2 plus under these conditions would form a carbocation. So I guess I thought it was implied that first I would turn it. Yeah, you see what I'm saying? I guess I thought it was either implied that I would turn it into this leaving group first, or this leaving group first. Excuse me.
Okay, that makes sense. Thank you.
No, I'm sorry. Yeah. Sorry. All right. Questions? Any more questions?
I have one question. Can you scroll up to the previous problem that we worked on? So
This
for
one?
this one, right, yeah, that one right there.
Okay.
When we're going to the left side, I know this is specifically SN2, but is there a way we can get to that product with the double inversion using like ether reactions?
Ether?
Yeah, because like what I see is like, I don't know, there's OH.
Well,
and then there's like another.
No. And let me explain to you why. I see what you're saying. If I gave you this, I see what you're saying. I see your question now. If I gave you this to this, oops. Oopsie. Yeah, sure, you're in business. You can totally do a Williamson ether synthesis here. Use this. And so first step here would be what? Okay, deprotonation, hydride would come in. You would form this guy here. And then second step would be what? My alkyl bromide in this case would be ethyl bromine. And so that would work for an ether synthesis. Okay, and that would be that. But for what I gave you, okay, you can't do this for reasons that you'll understand next semester, but I can't do 1 NaH, 2 that. What is this? It's an acid chloride. And they,
okay.
yeah, you see what I'm saying? There's no, it's called an
I
acid.
got you.
Yeah, and so, yeah, if I gave you a Williamson ether synthesis, no, this is a great question. I'm glad you asked it. If I gave you a Williamson ether synthesis, yeah, you're in business because you never have to break the oxygen carbon bond, right? Yeah, so anytime you break that bond, you're either going to form an inversion or you're going to get a racemic mixture. But yeah, so this, yeah, you don't know how to do this yet. And it's not as straightforward as you think.
Okay, thank you.
But that was a great question. Thanks for asking it. Okay, so the next thing we're going to talk about is is ethers. Speaking of ethers, so, and I just showed you how to make them using the Williamson ether synthesis. So thank you for that glorious segue into the next topic. Okay. So ethers are what I'm going to talk about. And the only really thing we're going to talk about them undergoing is substitution with acids. And so again, substitution, when I talk about acids and alcohols and ethers, all I'm talking about is my halo acids, HCl, HBr, HI. I haven't used HI. First step, always is protonation of my, I can be a base oxygen atom. Okay, let's get this over. Okay, and so if I can, I'm going to undergo an SN2, I'm going to undergo an SN1 reaction. And so again, we have to determine what's going to be our leaving group and which substrate is going to form our carbocation. And so if I look here, this oxygen here, which I kind of drew kind of crappily. Here, let me clean this up a little bit. Oh, I guess it's a different color. Oh well, shit happens. Okay, this carbon here is a primary carbon. This carbon here is a tertiary carbon. So I've created my good leaving group. Okay, and anytime it can undergo, anytime it can form a carbocation, it's going to form a carbocation. Okay, and so as a result of that, I know that this ethanol group rather, is going to be my leaving group because now I have this. Tertiary carbocations we can form all day. Okay, and then of course the second step, iodide is going to attack, and so it's going to go over here and form this alkyl iodide plus ethanol. Okay, if I give you the exact same reaction and I tell you that there is an excess, what do you assume? More than one equivalence. Okay, everything is the same. But then the excess iodide will start to react with the lesser substituted alcohol, and it can also undergo a substitution reaction. Of course, its reaction mechanism is going to be SN2 because it can't form a primary carbocation. So in an excess, you have both of these alkyl halides formed. When I have one equivalence, I form the more substituted alkyl halide and the less substituted alcohol. Questions?
I have a question.
Yes.
In the book, I think it says something that like hydrochloric acid can't do ether reactions. Is that correct or no?
I'm sorry, say that one more time.
That HCl isn't strong enough for ether reactions, only HI and HBr are. Is that correct?
I mean, she says a lot of stuff in this book that I don't necessarily agree with. Like, you don't need purity to do chlorination with thionyl chloride. Trust me, I've done those before. That guy's good on his own. I did not read that. It'd probably be a lot slower, but it's still pretty strong. Chloride isn't the greatest nucleophile, so maybe it'll work in some conditions, and maybe it won't work with other conditions. But I've never had a problem with it. But then again, I've never done highly substituted reactions like this, so must have been something she's added in the 6th edition. Oh, there it is. Only HBr and HI. Wow. Yeah. Okay. Yeah. I don't agree with that. I know that's not what you want to hear. You want all chemists to agree on everything all the time, and you want everything to be nice and orderly. I've done this reaction with HCl, but I did it with HCl in this. We were bored one day in lab. I'm a grad student, And so we did this. And then we distilled out the alcohol. All right, moving on. Any more questions? Sulfides are pretty self-explanatory. I'm not going to go over those. The only mechanism you need to know for sulfides are pretty much the same things as I did with alcohols. Okay. Disulfide mechanism, like if you notice when I talked about the disulfides, I didn't really give you guys a reaction mechanism. That's because that reaction mechanism is beyond the scope of this class. So just know that it happens. That's all you need to know, is that it happens. Okay. And so now what I'm going to do is I'm going to go ahead and talk about my epoxides. And I know she talks about the synthesis of epoxides, but I'm not going to ask you about that until next test, because we're going to be talking about ethers, and ethers form species that make epoxides. So 1, okay, a nucleophile, it's got to be good. 2, water, okay, this is basic. So I'm going to see what the least subbed. So I'm going to add, I'm sorry, let me give myself some stereochemistry here. I'm going to add to the least substituted carbon. Obviously, I'm going to maintain my stereochemistry. Why? I didn't do any chemistry to that carbon. Then I'm going to use HA over here. So obviously, this is under acidic conditions. Oops. I'm going to add my A here, OH here, and then I'm going to have inversion of the chiral center. Okay. And so, again, a couple of things you need to take note of for this. Stereoselectivity and regioselectivity. So this reaction is what we have, regioselective. And it's also stereoselective. And so this is a nice reaction because it gives us all sorts of control. As you're learning now, there's a lot of different byproducts in organic reactions. We have to clean those things up at the end of the day. And sometimes it's very difficult to to separate molecules. So this is a nice reaction. And so again, the mechanism for this, very simple mechanism. Okay. I'm going to react this in the presence of this alkyl sulfide to water. Again, anytime you have an alkyl group, you know it's what? Basic. So just cross that out. Regioselectivity, because I don't have anything helping to direct the sulfide. So both of those carbons are equally charged. And so it's going to go through the path of least resistance. So it's going to go to the least substituted carbon. Making sure that I don't drop my carbon. I'm going to remember to draw my bond here. Hydrogen, of course, is going to be, I'm sorry, water, of course, is going to be my source of proton. And so this is the structure here. Okay. All right. Something we have to worry about with rings, cyclic epoxides. Okay. H2O. Is that we're going to have we would so-called trans addition or anti addition. This is my alkyne. Acetylide anion is going to be formed. It's very basic. It's going to attack the top of the epoxide ring. Okay. And so the intermediate species I get here is going to look like this. And so what's key here, and this is going to look weird, but this is how you draw it. Okay, that's what I'm going to form. Okay. By the way, guys, be careful with these SP. If you draw it like this, you'll get points off. If you draw it like this, you'll get points off because why? It's linear. So be careful with that. Make a note. Make a note so you don't get any points taken off, because I will take a point off if you have the wrong bond angle. Protonation step. Formation of this species here. Questions?
This might be dumb, but why is there a wedge on the second one? Like the one with the base?
Here. So the one you're asking me about?
Yeah.
Yeah. So again, if you have an epoxide, right? And so I've got my epoxide, it's kind of like a dash, so it's going down like this, right? So it's coming, I'm the cyclohexane ring, and my epoxide is like this, right? And so what it's doing is it's blocking a bottom side attack in this case. And so my base has to come from the top. And so it's going to be this. So this step right here is what we call anti-addition.
Okay.
And so if this is my epoxide is on a dash, then my nucleophile is going to attack and be on a wedge.
Got it.
You're welcome. All right. Any more questions about this? All right. So let's look at this. Yes. That's okay.
Do we have to, so when we're doing the test, do you want us to show you the acetylide synthesis?
Yeah. Very good on the pronunciation. That's not an easy one. Yeah. I want to see that.
Okay.
Yeah.
Why is there a hydrogen attached to that triple bond in the first step?
In the first step here, this is a terminal alkyne, right? And remember that carbon, so right, there is an implied carbon here. And we know that carbon has to have 4 bonds. And so that hydrogen is making up the 4th bond.
Okay, so there's like a triple bond like that, you know that there's a hydrogen and you have to
I mean, yeah, so typically we would just draw it like this, right? And then the hydrogen would be implied. But I drew the hydrogen because, you know, it's part of the mechanism. So yeah, you this goes back to knowing that the carbon has 4 bonds. And then if I have this terminal alkyne here, we remember that the pKa of this hydrogen here is 25, which is why we can remove it so easily. So yeah, like if I have an internal alkyne, I can't do anything here because why? There's no hydrogen here. If I put a hydrogen here, I've exceeded carbon's octet, and we don't do that.
Okay, and then for sulfides, what did you say the only mechanism we need to know for it is?
I didn't say that.
Oh.
You need to know all the mechanisms I've shown you, every single one of them. And we see sulfide present in thionyl chloride and all the sulfur. Oh, I'm sorry. You're talking about the thiols. Okay. This, which would be the exact same as if that sulfur was an oxygen. Same thing here. So it would be same types of reactions as if sulfur was an oxygen. Right? Okay. Sulfur is just underneath oxygen on the periodic table of elements. So my ass is starting. I've been sitting in this chair since 9 o'clock this morning. Ugh. All right. Any more questions? All right. So epoxides under acidic conditions. So again, now we have regioselectivity, and that my nucleophile, which can be neutral now, will attack the more substituted carbon. Again, I did a pretty good lecture over that. So if you're uncertain why, go ahead back and watch this lecture. Okay. But now I'm going to detect the more substituted. I'm going to open up my ring this way. Okay. I am going to see inversion, but like I told you guys before, if you just draw it like this, okay, it's a lot easier not to make mistakes. If you were to do this reaction right here, do this mechanism, and then try to draw it neater, okay, and you showed me this wedge here, this is actually wrong because you flipped over, right? You rotated that sigma bond. And so if you're really fancy and you know why, this is how you would redraw this methyl group once you rotated and attacked. But again, it's very easy to make a mistake, and so this is why I have you guys draw it like this. Okay? Does anybody have any idea what I'm talking about right now?
You want us to draw it like which one?
This one. Yeah. All right. Next step, of course, is deprotonation. Oops. Ethanol. Whatever your nucleophile is, can do your deprotonation step. And so this is, that's your final product. All right. And so acidic versus basic conditions. Acidic versus basic conditions. So say I have you guys starting with this epoxide here. And I want you to make this. It's ugly. Okay. I want you to take the same epoxide and I want you to make this. Okay. Both of these, I added a methoxy group. Okay. Both of these, I added a methoxy group. But what you notice here, this one to the left, I added the methoxy to the most substituted carbon. Okay. The one over here, I added to the least substituted carbon. And so how could I put the same substituent on here under these conditions? So let's do the one going to the left. You guys tell me. Acidic. So I can just write this down and I would expect full credit. I mean, I know you guys will, but you're not getting full credit. What else? What needs to be my nucleophile? Tell me what my nucleophile needs to be. Test your knowledge and don't be afraid to be wrong. No, water? Does water have a methyl? Say again?
Methoxide?
If I use methoxide in the presence of this acid, what's going to happen? I'm going to form that. Methanol. Whoever said methanol, you're correct. MEOH. Okay. Don't use water. You guys have this idea that water somehow it's, good job, Miles. you guys have this idea that somehow you can just dump water into a reaction and magically whatever you want comes out on the other side. Guys, if that was the case, I mean, every time we had a rainstorm, Lord knows what would happen outside, you know, freaking trees turned into tires and shit. Okay, it's not what happens. Okay, and so, and I'm not going to give you one where you just add water because I know that's what you guys are going to do. Okay, and so you just need to recognize that this is a methoxy group, and if I add water, how the hell am I going to get a carbon and 2 extra hydrogens there? It's not going to happen. Okay. And again, under acidic conditions, you can't use a base because why? Well, the base will be neutralized by the acid. And now I've got this with nothing to catalyze my ring here, right? Now that my protons have all been sucked up by methoxy, they're not free to go protonate the neutral epoxide, right? Because this is gonna suck them all up because it's a much stronger base than the neutral epoxide ring. What about this next one? Everyone's like, again, there's a CH3 here. So if I'm going to use hydroxide, this does not equal a CH3. There's no CH3 here, but you're close. Methoxide.
Sodium methoxide? Oh.
Now is the time for sodium methoxide. Very good. And so you can write it like this. You can write it like this. You can write it like this. Hopefully by now you now know that all 3 of these are the same thing. And of course 2. Don't forget your water workup. And guys, I cannot stress enough how you have to remember your 1,2s. 1,2s. Okay. And so I don't have to worry about sodium methoxide reacting with an acid because why? I'm not adding any acid here, right? So this is basic condition. So this will work. Okay, this will work. All right. That's about all I have for you guys. So I am opening up the floor to any and all questions right now.
Ethers do only SN2 or do they do SN1 too?
They do SM1, and it just depends on what I give you. What I told you guys up here is if I can undergo an SN2 reaction mechanism, I will. I'm sorry, an SM1. So it's kind of weird. It starts off doing an SM1 because why? I formed this carbocation here. But then the second part is SN2. And so it depends on what the substrates are, right? This is tertiary, so it can form a carbocation. This is primary, so it can't. This one that I was telling you about, what me and my friends did in our research labs when I was a grad student, this would be SN2 followed by another SN2. And so again, you have to be aware what types of reactions can a given substrate undergo. As far as alcohols go, okay, methanol doesn't do any substitution reactions, but it only does E2. Primary, SN2, E2, depending on what acid's present. Secondary and tertiaries, SM1 and E1, depending again on which acid is present. And so again, you have to be able to tell what type of species, intermediate species, can be formed given this specific substrate. Okay. Oh, thank you. The group me question. Hold on. So Paulina asked me this question on the group me. Let me go in there real quick. So it's kind of fuzzy. So I can see the structures, but I can't see what it says off to the side. Paulina, can you read to me what it says? So you're talking about this guy here?
Oh, sorry, which part were you? Oh yeah, for that one, but there's also the second one. Why I didn't understand for the second one, for B, I didn't understand why, I mean, I know it says explanation, but when I was doing it, I still, didn't see why.
Didn't see why what?
It was that there were two sticks because it's an achiral chiral. There
Yeah,
was
does it end up as 2 sticks as well?
in the first C it didn't end up like that, so then that's why I didn't understand.
Wait, I can't honestly. This picture is really fuzzy. Tell me if what I'm writing is what is on the book. Is this correct?
Yes.
Yeah, and the reason she does this and she doesn't use any dash and wedges is because you start with an achiral center and then you end with an achiral center. And so that's why dashes and wedges aren't really appropriate here. Does that make sense? So again, if I were to draw this species like this, I can't assign R or S. And so I could have just as easily drawn it like this. And so these are the same. And so typically what we do is we'll just draw them without any stereochemistry implied because there is no stereochemistry. Does that answer your question?
Yes.
And then you sent me another picture.
The picture was from the textbook, from the answer key and from the textbook.
Oh, I see what you're asking. She started off. Oh,
She started off with
that little. See, she doesn't have any idea how much this confuses you guys. She starts off. Okay, so here's the deal. I'm going to tell you what happened here. I know exactly what happened here. She wrote the question in the book, and I've done this before. I've actually helped to write textbooks, and then somebody else wrote the solutions manual. It's a shitty thing to do. Okay, but you know, hey, I know that doesn't help you out as a student who's trying to figure out what the hell is going on right now. Yeah.
So no, I thought that maybe I missed something or I didn't, or something that you explained that I didn't catch.
No, you didn't,
so then
you
I
didn't
was
miss
like,
anything.
okay.
You didn't miss anything. All right, so let's see. Will acids be always a one step on the epoxide reaction? No, and as a matter of fact, none of the epoxide reactions are one step. None of them are. Okay, I have step 1 here. Addition of the proton. Then I have nucleophilic attack here. And actually, for this particular one, I have a deprotonation step. So it depends on what you have. Okay. And so even with under basic conditions, okay, I have nucleophilic attack followed by a protonation step here under basic conditions. So all of the epoxides are 2 steps minimum. You're welcome. Can you post a previous exam or a sample exam? No. I'm slammed right now. I'm sorry. I am absolutely slammed right now. I don't have time to do that. I'll be writing your exams. For the last question, can you tell, how can we tell if it's an acid? No, I'm not understanding your question. Can you elaborate on that?
Yeah, so I was just wondering, how can we tell if it's in acidic conditions? Will that info be given to us, or?
Oh, I have to tell you that.
Okay.
So I'll either write HBr, so you need to know your acids, right? But you should have known those because you all graduated from general chemistry. Or I'll give you H+, right? So if you see H+, you also know it's an acid. And of course, the only other way I could draw it would be like this. So hydronium. Hydronium. Okay.
That makes sense. Thank you.
You're welcome. All right. Are you guys done with me?
I have a quick question. Following up on the one that was sent to the group me, I just want to make sure I understand. So I understand that the final product with the bromine is achiral. I guess where I'm getting confused is C starts off with the same stereochemistry.
B as in Bravo.
C as in car.
Okay, C.
Yes, so it has the it's being reacted with the hydrochloric acid, and but the solutions manual says that one is racemic.
It
So I'm
is.
getting okay. I
Because
guess go ahead.
No, go ahead. Finish up.
I guess I'm getting confused as to why this one's racemic and the one before with the bromine is not.
Achiral. So when I do this reaction here, right, I'm going to form this guy plus this guy. All right. And so I'm going to have a 50-50 mixture of my R and my S enantiomer. That is by definition what a racemic mixture is. And yet when we go up here and I form this compound here, right? So I am going to form this guy and this guy, but who gives a shit because they're the same. In other words, it's non-chiral, and so it's non-chiral. So by definition, if it's not a chiral species, it cannot have an enantiomer. If I can't have an enantiomer, I can't have a 50-50 mixture of two enantiomers, so then it can't be racemic.
Got it. Thank you.
Sweet. Yeah. Words have meanings. Words have meanings. All right. Anybody else have any questions for me?
I have a
All right. Yeah.
In the book when it talks about like sulfides and stuff, one of the products is like a sulfonium ion, which is charged.
You're cutting in. Hey, dude, you're Sam. You're cutting in and out. I'm only getting about half of what you're asking me. Sam, I think we lost Sam.
Yeah, my bad. I don't know if you can hear my internet's kind of bad, but in the book when it talks about sulfides, one of the products is sulfonium ions, which is charged.
Yeah.
I wonder if you'd see something like that, because usually you don't.
I mean, you might. I mean, you guys all want to be doctors and shit. You're gonna see that in biochemistry class, so yeah, you might. Anything I talked about in my lectures is fair game. Anything I talked about in my lectures is fair game. If I didn't talk about it in my lecture, though, and it's in the book, other than physical properties, you're not going to be tested over it. All right.
Professor, I had a question.
Yes.
So you're in your first example on the ethers problem, where you reacted it with HI.
Uh-huh.
Can you explain why the leaving group with the tertiary carbon is a leaving one and not the primary?
Yep. So we have a couple of options here, right? So, oops, I didn't even cut this intermediate species here. Oh, well, that's cool. And so I have a couple of different options here. Once I've protonated this, okay, I can do one of two things. If I have nucleophilic attack of this primary substrate, it has to be SN2, right? Has to be SN2. I can't just get this guy to leave and form this guy here, because why? Because we do real chemistry at UTSA and we do not form primary carbocations. So that is not an option, okay? Remembering that this is taking place, hydroiodic acid is in what solution by definition? Aqueous. And so what's going to happen to the iodide? So we know that this is my iodide anion here, right? And so we know it's iodide here, okay? And so what's going to happen is it's going to get caged. And so we don't see any SN2 reaction, because why? While this iodide is trying to break through of this hydration shell, okay, this other part over here is just going to be like, bye, Felicia, I'm out. Okay, and so it's all about two different rates of the chemistry. right? What's going to happen first? I mean, yeah, if I couldn't form a carbocation, eventually iodide would do a substitution reaction, an SN2, but this is going to happen much faster than this happening here. Okay, iodine's not going to break through. And so because these two guys are basically racing to see who's going to get to the finish line first, that tertiary carbocation is going to form much faster. Excuse me, that's why we don't see any SN2. Thank you. Sorry about that. I got the COVID-19 thing. What I wouldn't do to be put into an induced coma for the next 3 weeks. Just kidding. All right, any more questions?
Could you talk about how a disulfide is formed, or like what kind of reaction it goes through? If that makes sense.
We don't talk about that. You just need to know the reagents. The mechanism is not a mechanism that you guys need to know about. It's beyond. We don't even talk about that in organic 2. It's pretty weird. So just know the process that disulfide is formed, the reagents that are present. Nope. All right, great. So you guys study, have a nice weekend, and I'll be sending out some emails regarding the exam. Hopefully everybody's figured out how to upload a PDF, so that would be wonderful. If you have any individual questions, you can send me a message, but I still have to write your exams, so I'm going to be pretty busy today. So take care. Talk to y'all later, and I'll post this as soon as it's done processing. Okay? Okay. You guys are welcome. Have a nice Saturday.